Our next speaker is an Azure Global Black Belt for DevOps. Helps Microsoft clients create reliable infrastructure and code deployment procedures. Has run the DevOpsDays Chicago conference, which is probably a lot better than ours. And has recently published a book on serverless computing in Azure with .NET. Her name is Sasha Rosenbaum, and she's here to talk to you about CI/CD for machine learning.
Thank you, Mario. OK, so I see some folks are still coming back. So we're going to play this awesome animation just for kicks. So this is so there's no screen in front of me, so I'm going to be turning around a lot. I'm sorry about that. But in general, this is an animation of a AI learning through learning to walk and obviously being challenged by some obstacles, right? We're not going to talk about this, but we're going to mention this as an example, right? So I'm going to introduce myself. Mario stole all of my thunder, but generally, I'm Sasha Rosenbaum. I work for Microsoft. I'm a Microsoft Azure Global Black Belt. It's an awesome title. Nobody knows what it means, but it sounds really good, right? Generally, what I do is talk to a lot of customers about implementing DevOps and getting better at delivering software with DevOps on Azure platform, right? So that's the primary. I am a co-organizer of DevOpsDays Chicago. It's a great conference, not so far from here. You guys should come next year. And I did recently publish a book on serverless computing in Azure with .NET. It sounds narrow. It only took me like 400 pages to describe the basics, like really basic stuff. And it was published last year, so it's about only 50% outdated now. So you can still learn something useful from it. So that's cool. But really, I don't have a data science degree. My background is computer science, and I've been a developer for many years. And really, the reason I'm here is that I've been building things with technology for 13 years, and I really care about DevOps, right? And so in terms of when we approach, so basically when we approach new fields, this slide is intentionally blank, right? When we approach new fields, we often forget the lessons that we learned before, right? So we tend to do this over and over again, and we certainly did this with ML. But I wanted to come here today with solutions and be like, hey, this is how you do CI/CD for machine learning, right? But the more I dive into this field and the more I look at the stuff that people have, the more I realize that the field is pretty vast. Different people are doing different things, and there's still a lot of learning to do. So basically, I think maybe I'm coming here more to ask questions than to give you all the answers. But sometimes discovery is all about asking the right questions. And speaking of asking the right questions, while a lot of people are coming back with their coffee, I did introduce myself, but I would like to learn a little bit more about you. So raise your hand if you are a developer. All right, cool. Raise your hand if you are ops, DevOps, site reliability engineering, something. OK. And some overlap between the two. That's cool. If you are a DBA or something similar, not a lot. Security, DevSecOps, like 3 people showed up. That's cool. If you're a data scientist or doing a lot of work with machine learning of some kind. OK. Did I have any hands? Can you do this again? Data scientists? OK. I got a couple. OK. Cool. Awesome. OK. And then everybody else, like PMs, maybe analysts, anybody I forgot? Cool. OK. Incident commanders. So I did see probably like 1 hand go up for data science, maybe 2. So for sake of everybody else, let's start with some definitions. It's usually helpful. So I'm going to try to define artificial intelligence. This is kind of hard to do, but in general, artificial intelligence is the theory and development of computer systems that can perform tasks that usually require human intelligence. So anything from image processing, natural language processing, translation, things like that that we think of as complicated tasks. This is something, if we can do this with machines, then we call it artificial intelligence. And then AI systems usually do this through processing large amounts of data and recognizing patterns in that data. Right? So that's like the most important thing probably in artificial intelligence. Now, artificial intelligence is here. It's a growing field. It's existed for many years, but we are now seeing a lot of entrances into different fields. And really, a lot of our lives is already being ruled by algorithms that we don't even think about. But I'm just going to give a couple of examples of what AI can do today. So in fashion industry, there's a lot of work that's usually done for like the next year of fashion. So the fashion industry both creates trends and tries to identify trends so they can stay on top of the line and sell you the best color for next year and the best shape and the best whatever. Right? So right now, a lot of algorithms are being developed to basically replace humans who were doing this work before. There's AI that predicts what color it's going to be, what shapes it's going to be, even creating the clothes themselves, so like creating the actual fashion design. And also, we traditionally think of creativity as something human, but there are a lot of art, music, even movies right now being created by AI. And they're sometimes completely indistinguishable from human creations. So this stuff is interesting when you start to dive into this. But also, if you thought your job is safe, so Microsoft, in collaboration with the University of Cambridge, created a deep coder, which is an AI that can write code. Basically gets fed by a lot of coding samples from the Microsoft database, and then it can create simple code programs that can compete in coding competitions. Now, this is very basic right now. It doesn't do a lot of stuff, but it's easy to see how we can, in just a few years from now, potentially have algorithms that can develop pretty reliable and pretty good code. So we define this now. We can get narrower a little bit, right, and say, what is machine learning in this space? So machine learning is a subset of artificial intelligence, which is focused on basically this is the definition that I like most, right? It's getting computers to act without being explicitly programmed. Right? And you do this through learning from a lot of data, identifying patterns, and then making decisions with minimal human interaction. So when people pose questions like, oh, what happens if a self-driving car sees a human, how it will decide if it averts or if it doesn't decide in the sense that we think about when we think about programming decision models with if and else statements. Like, if I see a human, then turn left. No, right? We are learning from data. And so whatever's in data is going to be in our algorithm. So there's a bunch of different types of machine learning. We're not going to go into this, but most people right now are here. So most people are in supervised learning, which essentially, we can describe this as we get lots and lots of labeled data, then we train the model, we discover the optimal model for the algorithm, and then we predict, basically, the labels for the new data. So basically what I'm saying is, first of all, we have to start with labeled data, right? If we didn't have labeled data, we can't build something that learns from it. So before I say, everybody likes to give the example of cats and dogs, before my ML algorithm can identify who is a cat, I first have to give it lots and lots of pictures of cats and not cats, and say, hey, this is a cat, this is not, this is a cat, this is not. And my data has to be also good for it to be able to derive some sort of insight from it. And then once I develop my model, I can predict, so I can give it a new picture of something that's a cat or a dog, and it's going to tell me, hey, this is a cat, right? And it may have some sort of percentage of accuracy. So if you've studied statistics before. This might be familiar, right? This is called linear regression. So let's say this graph is for predicting housing prices based on the square feet, based on the size of the house, right? So this tries to discover a simple formula, which is y equals a plus bx plus epsilon, which is an error. So basically, what I try to do is discover a and b such that this line will predict the new dot. So when I give it the x, right, the input variable x, it can tell me, okay, your y is going to be over here. So this is like, you don't have to get into machine learning for this, but this is actually, so a lot of the stuff that people are using today in machine learning is about this, right? So it's linear regression or logistic regression. So it's not, the math is not so complicated as people think, right? But obviously this has limitations because I only have like a single variable in here, right? So if my house price obviously depends also on like, okay, where is my house located? What's my neighborhood, right? So it's not a single thing that potentially has influence on my price. So if I go into more complicated things, that's why this is all the rage, right? The deep learning is a subset of machine learning, which uses deep neural networks. And here we can get into like having multiple layers and multiple inputs, and all of these variables are going to influence the output in the end of it. And each one of these nodes will compute a formula. So I have lots and lots of functions in there that are being computed. So like from that regression, which had a simple formula with one set of parameters, I'm getting into like tensors. So matrix with lots and lots of rows and columns, right, and different layers. It kind of gets hard to visualize as well. But these algorithms, deep learning is really good for complex problems, especially when you have a lot of data. So like complex problem like image processing or natural language processing would be great for deep learning. But it's not, so I wouldn't say this is the most commonly used thing. Like obviously, people who are building the self-driving car are using a lot of deep learning. But a lot of people out there are doing simple predictions, such as the pricing, say the stock pricing on the market, which may have one or two input variables, and proceed from there. So now that we have, this is when. So this is what the computation for this looks like. It's sort of this forward propagation, backwards propagation. This looks very scary. This is for some, deep learning algorithm. Scary, right? So I don't know. It scares me anyway. We're talking about data science here. So why do we need this DevOps thing for data science? This all sounds like math and stuff. Well, the thing is that basically, what it ends up being is people writing code, right? And putting that code into an application that is software that's served to the clients in this way or another, right? So we still need a process to be able to reliably deliver it. So now, question is, how do we do this? Because when we get into new fields, we often forget what we learned before. So when we got into software, we're like Casey mentioned, has nothing to do with engineering. No, it's a completely new field. Has nothing to do with construction. We got nothing to learn from you guys. And we discovered that we do things like this because people don't talk to each other, and they build things, and they then come into the outcome that, this to me is a description of why Agile matters, right? So that we don't get into this long process where we built things for months, and then we didn't know where we were going with this. Now, this also happened in serverless. That is recent development. But first, when serverless first started being popular, people were like, oh, no servers equals no ops. That's not a problem at all. Just put your zip into production, zip your code, put it in production, it's going to work. It's going to be great. I'm not going to dispute him in the first part of the no servers, but I think, Tom's going to talk to us a little bit more after lunch about, DevOps for serverless. So basically, the reason we need DevOps is I definitely have no problems in this space because my code always works. So when I write my code, from the first try, It's like, I don't need no unit tests, like, I don't need no source control. I'm just like, perfect from the very beginning. Not only that, like, I anticipate all the changes that my clients will ask me to do like a year from now, and I put them in the first version. It's like, great, right? And then I could just, put it in production. This also is true for my like data science models, because I never need to tweak anything. But well, for everybody else, yeah, DevOps is important because change is the only constant in life, and stuff happens, right? So let's get into like, how do we actually do this for machine learning? And here's the challenge. So lots of people are using lots of different tools, and so I put a lot of things on this slide, and some of these are like, so programming languages, right? We have a bunch of different programming languages like Scala, Python, R. Then we have lots of different libraries that people are using, like scikit, like TensorFlow, some other things that are out there. And then like people are using a lot of different prepackaged software that helps them do this stuff, right? So the question of how you do CI/CD for ML is about how do you do ML first, right? Before you started doing CI/CD. So first option is maybe your ML looks like this. And so like your AI stuff can be powered by somebody else's APIs. There's, we do APIs, so they're called Microsoft Cognitive Services. Google does excellent artificial intelligence API. IBM Watson has a set of APIs. So all you need to know about this is that you make a REST API call, right? And then you get a set of outputs well described. So and then you can put it in production. And now your application actually has artificial intelligence, which is very, very advanced. But of course, it depends on your use case. So it might work in some cases, it might not work in some other cases. But basically, I dare say that if you're doing this, then this is a solved problem, right? Even though a lot of people don't do that, I know John mentioned that some people still don't have source control, and that really happens. I saw a quote yesterday from someone who's a developer advocate at Google, and he said, like, oh, DevOps is a solved problem. There's nothing else to develop in this space. It's all like table stakes. And I'm like, I don't know what companies you talk to, because I talk to a lot of people who have a lot of like real world struggles in implementing. Yes, maybe the procedure is out there and it's described, but it's not always so easy to actually get it to work. But in general, like we have a lot of insights, we have a lot of knowledge about how to deliver code into production. Now, if we get into this, so the other option that you have is using somebody's tools that provide you with like visual a representation of your ML model. So this over here is Azure ML Studio. It's a drag and drop, and then like it learns, and you create your model like this. There's open source tools that do the same thing. I couldn't get a good screenshot of them, so that's why it's this. But in any case, in this case, so these tools will do some good for you, right? They will fix some of the issues. They will do some of the procedure for you, but then you kind of depended on what the vendor thinks your pipeline should be, right? Because you don't have full control over how this stuff is getting then into production. But it might be that your vendor is absolutely great, or your open source software is absolutely great and works for you. But then we come to like probably the most people who are implementing ML right now. Their ML implementation looks something like this. So all this complicated math is written in code, and it's very often people use Jupyter notebooks or Zeppelin notebooks or whatever. People also often just develop Python scripts or R scripts or whatever it is. So it's basically just code files. So this is the interesting case, because a lot of folks right now have this, but don't have any sort of deployment procedure that would allow them to have a repeatable, reliable process for delivering this into their application. So this is kind of the case that I want to focus on. And then, so basically, like this is the flow. So this flow will kind of guide us also through like how the CI/CD pipeline might look. So you start with data, right? And then you go split your data into the training set and then the test set, right? So this is both sets of labeled data, but we can then use the training set to train the model. So, hey, this is a cat, this is a cat, this is not a cat, right? So then the model kind of sets on the parameters. So let's say, it's WB or whatever. It's a set of different variables with different values that will calculate then what the outcome is, right? Then I submit a test set into the model, and I say, hey, is my accuracy any good? Right? So there's ways to estimate the accuracy of my prediction, and it also depends on how complicated the model is. But basically, if my accuracy is not good, I go back to the training, and I either try a different algorithm, try different algorithm parameters, or I try basically more data. Or like I say, OK, my model is ready. I'm ready to put it in production. So if we take it to the next step, this is basically, so now I have a confession to make. Before I go there. I wanted to come here with a demo and be like, hey, here's how you technically do this. But I spent my last 2 months on a plane, not the same plane, different planes, different cities. It's kind of hard to build cloud demos on planes, so they didn't work as well as I wanted. So I will talk to you about theory, and I promise you practice. So it's my goal in the next couple of weeks to publish a couple of blog posts with kind of step-by-step guides on how to actually implement this. But we can talk about how this flow actually looks like, right? And then, so we have 2 entry points. In regular code, we typically have 1 entry point. Here we have 2 entry points. So 1 entry point is my model code changed, right? So I made some changes to my actual script. And then I obviously get to push it into source control. Now, most of our customers stop here. That's the extent of the DevOps for ML. But you also have another entry point, which is you push in data. So obviously, you need to make your data accessible to your computational cluster. So basically, you push your data into storage, some kind of storage. It's usually cheap storage, because usually there's a lot of data. And then you also need to take care of the splitting it into training set and test set. OK. Let's say we figured that out, and our data now is in storage. And that process, both of these processes obviously can be automated fairly easily, although you do need sometimes to consider how big your data set is in terms of like uploading to the cloud or something like that. Then you push it basically into the compute cluster. And that typically people use Spark over here, so some version of Spark, maybe Databricks or something like that. But you can also run on any type of computational nodes, so like Azure Batch, AWS Batch, container instances, so anything that can scale out to give you a lot of compute power. And then again, it depends on how big your computation is, because some computation can take half an hour, some computation can take 2 weeks. So just kind of figure out which one's the best, because some tools are more expensive than others, and some tools do better job than others, right? So that's a cost-benefit ratio. And then once you got your stuff uploaded here, you basically have your automation server, and then you can use, again, people use Jenkins, people use Azure DevOps, formerly VSTS. We have renamed it. It's great. Anyway, so basically you have the automation server that can take care of this process, right? So you upload the new code, right, from your model, and then you train the model, right? So you get that train data from here, and then you run your computational algorithm on your cluster. And then you test the model, and then you verify accuracy. Now, the most important part here is that your computational cluster has to support some sort of API, expose some sort of API that will allow your automation server to actually control it. Because if your computational cluster expects you to click buttons and there's no way to call it from outside world with an automated procedure, obviously you can't do this. So that's another thing to consider if you're choosing the technology to help you do this. So let's say you have your API exposed, and you have some way to get to your accuracy, and you have some way to basically continue testing until you're satisfied with the result. Now, let's say when I'm satisfied with the result, I'm going to push it to staging. So again, this depends on your application. because maybe your application just exposes an API in which you can submit data and will tell you the outcome. So like, OK, that's a cat, right? Or more live use cases like, I don't know, like direct marketing. So this person likes that. OK, this is great. But maybe your model is, you put this into code into your web application or whatever it is. Maybe it's on Facebook deciding which post you're going to see next. So the deployment process obviously is contingent on the application that you have. And then the last thing to mention here is I would probably put manual gates here more than I would in code deployment procedure, because the stakes are kind of higher. So especially here, let's say that computation runs on 50 cloud nodes of some kind, and it runs for a week. You don't want to kick it off unless you know that you want to kick it off, right? So maybe I added a print statement to my model. I don't really want to pay the cloud providers so much money. So probably you want to put a manual gate in here. And probably you want to put a manual gate in here because so maybe you're just trusting your accuracy scores, and that's enough. Or maybe you have someone who needs to say, hey, this model actually looks better than the previous model, so we want to update this, right? So this is your basic process. Now, I did say that I promise you guys practice. So if you are working on something like this, find me on Twitter, LinkedIn, whatever. Tell me what the use case is, because I would love to hear it, so I can basically, because like we said, this highly depends on what kind of use case you have. And I have a couple of use cases in mind, but I would love to hear what people are working on. So I would do us a disservice, and I don't know, I have time. I have 1 minute, 2 minutes. OK. So I would do us a disservice if I didn't talk about AI ethics. This is a big topic, actually, but it's important to consider. Like we said, our world is increasingly ruled by algorithms every day, right? And so algorithms are deciding what you see on Facebook. Algorithms are deciding if you get a loan. Algorithms are deciding if you go to jail. Algorithms are deciding a lot of things already today. It's not tomorrow, it's right now, right? And we as developers are now in control of what goes into these algorithms, right? And we have the power to construct AI responsibly or not. Now, one of the biggest realizations that I had this year was that bias is a property of information. So bias is really, we used to think about it as a property of humans. So it's about, humans discriminate against minorities, and humans don't like to generalize and apply stereotypes. But really, bias is a property of information because there's too much of it, right? So I can't apply a new process to every single thing that I do in my day. When I walk up these stairs, I don't think about walking up these stairs. I will apply the same process that I always apply, right? And then sometimes it screws me up because sometimes the stairs are not, the right height, and they don't comply to the standard. So basically, when you do this, when you learn reliable procedures from data, you will do whatever is in your data, and you will generalize from that. And that means that machines are actually going to be more biased than humans, because machines don't have a moral compass to tell you, hey, by the way, this sounds like a bad idea to discriminate against people based on the color of their skin. So we have lots and lots of examples. And again, bias is not the only problem with AI, but bias is a big problem. So I'm not going to go through them, obviously, but say a police scanner that decided if people are likely to commit a crime in a certain neighborhood or if people are likely to go to jail again. Both of these turned out to be highly racially biased, also highly gender biased algorithms that are out there. Basically, something to consider. If you feed your algorithm data that says that women are homemakers and men are CEOs, the algorithm is going to output the same thing, right? And the algorithm is going to suggest CEO jobs to men only. So, and this really happens, right? So, build AI responsibly. Thank you.
Thank you very much, Sasha. That was quite amazing.